Hello, today we're going to continue in our A-level physics revision series by looking at the subject of electromagnetism. We've already considered electricity, so now let's think about magnetism. What is a magnet? A magnet has a north pole and a south pole, and the magnetic field flows from the north pole to the south pole. Now, an important thing about a magnet and what distinguishes it from an electric charge is that whilst you can have an electric charge that is positive or negative, for example, a proton is positively charged, an electron is negatively charged, and you can have those entirely separately, you can never have a north pole on its own or a south pole on its own. Theoretically, they could exist, but they've never been found. In other words, you can never have a single pole. They always come together and the magnetic field flows from north to south. The Earth is in fact a magnet. It's tipped to one side, but its north pole and its south pole are here, and the magnetic field lines flow from north to south. And that's the reason that particles get trapped by the Earth's magnetic field. Magnetic field is sometimes called flux density, and its units are Tesla. You'll remember that in relation to charges we say that like charges repel, unlike charges attract, and it's the same with magnetism. Like poles repel. Bring two north poles of a magnet together and they will repel, and the reason is that their fields interact. They push against one another. Whereas if you bring a north pole and a south pole together, then the field lines readily go from north to south and create an attractive force. So, like poles repel, unlike poles attract. Now, a current flowing in a wire, here's a current I, flowing in a wire, will create a magnetic field around that wire. And which way does that magnetic field go? Well, we have to employ what's called the corkscrew rule. Think about a corkscrew. If you twist it clockwise, you drive the corkscrew into the bottle. If you twist it anti-clockwise, you pull the corkscrew out of the bottle. It's the same as a screwdriver. If you turn the screwdriver clockwise, you drive the screw in. If you turn the screwdriver anti-clockwise, you pull the screw out. And that's the principle we apply here. If the current is, for example, going into the paper, then just as the screw or the corkscrew goes in, that means if you want it to go in, you have to turn it clockwise, and so the magnetic field will go clockwise. If, on the other hand, the current is coming out of the paper, then this is coming out, then the field will be anti-clockwise. Now, if you put a wire carrying a current in a magnetic field, here is a magnetic field north to south, and here is a wire which you have to imagine is actually coming out of the paper, and the current is flowing towards me. What you will find is that there will be a force on that wire and it will move. And the reason is that there is a field between north and south, but there's also a magnetic field caused by the current going through the wire. And that magnetic field caused by the current in the wire interacts with the magnetic field that you've got on either side, and that will cause the wire to move. But in what direction? And here we have to apply Fleming's left-hand rule. If you take your left hand and get your thumb, first finger and second finger in this shape, that enables you to tell what is going to happen to the wire. The rule is very simple. Your thumb is the motion of the wire, motion. Your first finger, is the field, the magnetic field. Your second finger, second, for second, is the current. So thumb motion for first field, first finger field, and second finger current. And now if you line those up, you will find out in which direction the motion will be. So in this case the field is north to south, the current is coming, that's this finger, is coming out of the paper, and that means the motion, which is the thumb, is upwards. This tells us that the wire will be pushed up. The wire will be pushed in an upwards direction. In other words, there's a force acting on the wire. What is the value of that force? Well, the force is equal to the strength of the magnetic field, which we use the letter B to represent, multiplied by the current flowing in the wire, which is I, multiplied by the length of the wire, which is L. And it's important to notice that that L is not the entire length of the wire, but the length of the wire that is in the magnetic field. And you'll notice that in this example, the magnetic field B and the current I are at right angles, because the field is essentially going left to right and the current is coming out of the paper. So it's actually coming straight up at me, and that's at right angles. What happens if B and I are not at right angles? Let's suppose, for example, that B is in this direction and I is in this direction. What then is the value of the force? Well, the angle between the two is theta, and the force will then be BIL, the same as it was before, but now multiplied by the sine of the angle between them. And you can see that when theta is 90 degrees, the sine of 90 is 1. But when theta is 0, the force is 0. In other words, if the magnetic field and the current are both in the same direction, there will be no force. If we look at our left-hand rule again, this is with all of the fingers at right angles to one another. But if we take the field and the current, we can actually narrow the angle, but you'll notice that my thumb is still perpendicular. So where you have the field and the current in a particular plane, the force will always be perpendicular to that plane. What is the value of a field close to a wire carrying a current? In other words, here's the magnetic field around the wire carrying the current. By experiment, it has been found that the magnetic field is equal to mu naught I divided by 2 pi r, where mu naught is what is called the permeability of free space, I is the value of the current in the wire, 2 pi is just what we know pi to be, and r is the distance of the magnetic field from the wire. A solenoid is a coil of wire through which a current passes. And the magnetic field inside the solenoid is again given by experimental observation to be mu naught times n times I, where mu naught is once again the permeability of free space, n is the number of turns in the wire, and I is the current. There are ways of measuring the magnitude of the force. We could, for example, use a simple balance. Here is a balance. On the one side we can put weights so that we can measure the weight. On the other side we perhaps put a coil of wire around which a current is flowing, and we put that between a magnetic field, north to south. And there will be a force on that cable. In which direction will that force operate? Well, the current is going into the paper, the field is going in this direction, and so the thumb motion is down. You see the current is going into the paper, the field is in this direction, and therefore the motion is down. Let's apply the left-hand rule to this side, this part of the current. Well, the field is in this direction, north to south. The current is going downwards, and so the motion will be, my thumb, will be up. So here the force will be up. But I think you can see that on the other side, where the current is going in the other direction, the force will be down. And that will cause this coil to flip. It will rotate. Of course, it won't rotate very far, but if we arrange it so that we've got what are called commutators, that is to say, fixed gadgets, so that as this flips around, this wire will attach to that commutator and this wire will attach to that commutator, then you'll always have a current flowing up that line and flowing down that line. And so that will mean that this will continue to flip round. And if we put a little driver on here, that will drive something that will turn. And from that we've got a motor. Now let's think about the difference between charged particles in an electric field and in a magnetic field. If we take a charged particle, let's take for example an electron in an electric field. So here's two plates, one positively charged, one negatively charged. There is an electric field between the two. If you place an electron in that field, it's negatively charged, it will immediately move towards the positively charged plate. By contrast, if you take a magnetic field, here's north, here's south, and there is a field between the north and the south, and you place an electron stationary in that magnetic field, it won't move. It will stay there. But if you have exactly the same arrangement, the north and south poles with the fields, if now you have a moving electron, then that moving electron is the equivalent of a current, and you've got a current flowing in a magnetic field, and that will create a force on the electron and it will bend round in a curve. In this case, if we apply the rule of the Fleming left-hand rule, you will find that what the electrons will do is they will curve into the paper. So to recap, a charged particle that's stationary in a magnetic field won't move, but if it's already moving, then it will be curved by the force of the magnetic field. Now let's go back to our formula that said that the force was equal to the magnetic field times the current times the length of the wire. Current, we know, is the flow of charge per second, Q over T, where Q is the charge and T is the time in seconds. And the velocity of the charge is the length travelled divided by time, distance divided by time. And that means that T is equal to length divided by velocity, which means that we can now put in this formula here, we can say that I equals Q times T. Well, T is L over V. Sorry, I is Q over T, so I is Q divided by T, and T is L over V. So we now have that I is QV over L. But F is BIL. So we can now substitute this for I, and that gives us that F equals B times I, which is QV over L, times L. And of course the L's cancel, and so now that you've got the force is BQV, which is the value of the magnetic field, times the charge on the particle, times its velocity. Now we've just shown that a moving charged particle in a magnetic field will curve. So now let's have a look at, here's a particle which is moving but being curved in a magnetic field. And let's say it goes round in a circle of radius r. Well, we can say that the force on that particle is BQV. We just derived that. But we can also say that if anything moves in a circle, then there is a centripetal force acting on it to cause it to do so. And the value of the centripetal force is mv squared over r, when m is the mass of the particle, v is its velocity, and r is the radius of the circle. And those two have to be equal. And that means that bqv is equal to mv squared over r. And if you rearrange that, you'll find that r is equal to mv divided by bq. And this now gives us the capacity to separate out different velocities of charged particles. And the equipment we need to do that is an electric field. So we have two plates, perhaps connected to a battery, such that this is positively charged and this is negatively charged. And there will, of course, be an electric field between them. And we have a magnetic field which goes into the paper. And the way we describe that is we use crosses inside a circle. The idea is, think about an arrow. If an arrow were going away from you, what would you see? You would see the feathers of the arrow as it went away from you. So that symbol simply means that the magnetic field is going away from you. What would you see if the arrow was coming straight towards you? You'd see the point of the arrow. And that symbol means the field is coming towards you, out of the paper. That means it's going away from you, into the paper. So here we've got a magnetic field going into the paper and an electric field coming this way. And here we've got a stream of particles. Let's say that they're positively charged particles. What will happen to that stream of particles? Well, they're positively charged, so they will want to veer towards the negatively charged plate. But if you do the left-hand rule, you will find that the magnetic field, which is going into the paper, will cause them to bend in this direction. And if you balance the magnetic field with the electric field, then the particles will just go straight ahead. And what is that balance? Well, the force that applies to the particles from the electric field is E, the value of the field, times Q. What is the force as a result of the magnetic field? Well, we've worked that out. It's BQV. And when those two are equal, EQ equals BQV, which means if you rearrange that V is equal to E divided by B. So when the velocity of those particles is equal to the strength of the electric field divided by the strength of the magnetic field, then the particles will just go straight through, because the force of the electric field, which is trying to cause them to go that way, is exactly balanced by the force of the magnetic field that's trying to cause them to go that way, and they end up going straight ahead. And so you've got a velocity selector.